All right. Well, today I wanted to finish off our topics on talking about the physical transport of fluids as immiscible phases. And so the last one is today, 2.7. And after that, topic 3 is to dealing with mass transport dissolved in water, aqueous transport. And so what we've been looking at really is in being able to figure out, as you know, exactly where the distributions of these components are. We've wanted to be able to think of this as some kind of representative elemental volume, as it's often referred to. REV just means representative of the rest of the aquifer. And figure out maybe a couple of things. One has being what the saturation distribution is, both of the wetting phase and of the non-wetting phase. And not so much in terms of, well, both, I guess. Both in terms of what it looks like inside the place where it's saturated, or partially saturated, inside a region that's all red in this particular case. I guess that's not very big, is it? It can be bigger. But also the structure, if you like, that you'd expect to get based on the heterogeneity, and trying to understand the processes behind that. And our reason to do that is that we'd like to be able to figure out from the non-wetting saturations exactly how much mass is there. And if we know how much mass is there, we have some idea of the mechanisms that we might use to get it out. We know that if the saturation is relatively low, and we've worked on these two figures, which I'll draw again. You've seen these ad nauseum, I think, but let's do them again and do them on top of each other. You know it's going to be a relative permeability and a capillary pressure versus saturation curve for each of these. And so I guess for the non-wetting fluid, it is going to look something like this. And I guess I can draw, oh no, geez. Don't snap to a single curve. Oops. Should perhaps put axes on these things before we do it. Anyway, I think you probably know what the axes are. This is capillary pressure. This is saturation, which varies between 0 and 1 for water, and the opposite for the NAPL. And this would be relative permeability between 1 and 0. And I guess we have another fluid that's involved, probably do it as blue, and that would be something that would look like this. Right. And so this is the wetting. This would be the non-wetting. And I guess we know that in these circumstances, and I'll maybe do a thinner line, that if we, for instance, look at this glob here, or especially if we look at something that sits down here, then we know that the saturation of this is quite high. And in that particular case, if the saturation of the non-wetting fluid for that is quite high, then we'd be at this side of our figure. And in other words, quite rationally, if we looked at the relative permeability of the non-wetting fluid, it's almost 1. And so you could rationalize that if you try and suck this out, it will move because it's a continuous phase. There's not much water. It's all oil, and you're just sucking it out like you would petroleum out of a reservoir, or crude oil out of a reservoir. If you look at somewhere else within the system, maybe in this chimney, then you'd expect to be in a different saturation. So maybe I'll just outline this with this. And if we're in a different part of the saturation here, then you'd think that the relative permeability of the wetting fluid, in this case, is high. and the relative permeability of the non-wetting fluid is low. And so that if you try pulling a fluid through this, there's only one fluid that's moving, and it's going to be the water that moves. And so the only mechanism by which you could actually take out the red fluid in this particular case would be by moving water through it, making a plume on the downstream side, and dissolving it from its native single phase into the water, and then taking it out over time. And you'll do an assignment to do that that basically explores these concepts. So the two things, to get back to where we were before, the two things that we'd like to know would be something like saturations, and as a function of saturations, we'd like to be able to calculate volumetric flow rates, which we know are equal to a cross-sectional area, a relative permeability, which is a function of saturation, the actual permeability of the aquifer, and the viscosity of the fluid. Typically this is water that we're talking about here, and the pressure gradient that we apply across it to move it from upstream to downstream. And so if we know exactly what the volumetric flow rate is, we can also calculate what the mass removal rate would be. It would just be equal to the volumetric flow rate multiplied by the concentration, which we haven't talked about yet, but it will be that. And concentration, we made the point, is in units of mass per unit volume. And so the product of volume per unit time times mass per unit volume is mass per unit time, m dot, in other words. And so that's kind of simplifying everything we've done so far, really. That's kind of what we're aiming to do. So we're trying to quantify these behaviors by understanding the characteristic response. That characteristic response is embodied in these two very basic curves, which say something about the architecture of this and what it looks like, when you can remove one fluid versus another fluid, and how you can remove those fluids. So that's kind of a summary maybe of where we are. When we've talked about these different relationships defining saturation and capillary pressure and its impact on defining permeability, the permeability is impacted because the pore space is occluded as you start filling up with another fluid. That's the basic reason for that. We've mainly talked about it in terms of in the saturated groundwater flow regime. But we can also think of it directly in terms of unsaturated flow. And so that's what we'll kind of round out today by talking about with just some new concepts. So we've recapped things. I guess our main points were that we want to get saturation of the two phases. And if we get that, we can get permeabilities or relative permeabilities. And if we have that, we can get volumetric flow rates. And from that, we can get mass removal rates. That's kind of the sequence of things that maybe we're interested in. This seems very small, this pen right now. And so now we'll kind of back off from looking at that and look at mainly the unsaturated flow regime. And probably, I don't really want to do it to death, but I think it bears doing, is that the concept of matrix potential is what we'll use, and it's maybe a new concept, but it's actually not all that new. It is that we can define the total head within a system as equal to the pressure head divided by, pressure divided by unit weight of water in this particular case, the head and the elevation. So it's just a Bernoulli equation relative to some datum, right? So this is Z. If you had the water table up here, this is basically P over gamma W. And if the water is moving at some velocity V, then it defines, whoops, what did I do? Didn't stop me, you should have stopped me. Sorry. So we can always get the elevation where it's located. We can measure the pressure through something, piezometer, and usually this term is so small that we just ignore it. And so when we talk about unsaturated flow in the vadose zone, we usually use a term which is referred to as the matrix potential, which we'll call, I think it's psi, right? Which is psi. And it's a function of the volumetric moisture content. So maybe write that out, psi. Of volumetric moisture content. And maybe the first time we met, maybe the second time we met, we mentioned that groundwater hydrologists, petroleum engineers talk about saturations. Agronomists and soil scientists talk in terms of moisture content, which is defined not as a saturation, but as a volume per unit volume of the voids rather than total, of the total rather than the voids. And so this volumetric moisture content is just one way of being able to define that. And so all that's relevant, I guess, is that this matrix potential is essentially the pressure head. That's all it is, nothing more than that. And so if we come back to look at the behavior that we've already investigated, I want to come back to this, basically this figure here, just to reiterate that, because it is a kind of a key figure. And I'm just going to draw that thing out from the midpoint maybe to this, and this will be the ground surface, say. Nope. And on this side there'll be a couple of boxes, I suppose, and these are going to be capillary pressure versus saturation curves. If I can do it properly. And so this is going to be, I'll do it on the bottom first. It's going to be saturation of water between 0 and 1. And same on top. I guess saturation of the non-wetting, I suppose we could do in the opposite direction from 0 to 1. And this will be capillary pressure here. And the curves will look, you've seen them before, so you know exactly. I can't draw these freehand very well. But let's just draw one for now. And to draw the components. So blue for water. Too steep, sorry. Green for air. And red for Napple, I guess denser than water. So this is the deal. And so just to make the point that the capillary pressure curves that we've already dealt with, I suppose the one that we've been interested in the subsurface has really been one that is both, this is just the inverse of this upper curve, and actually it's really, and I'm going to draw it both red and blue because it represents the capillary curve between D Napple, so this is water, this is D Napple, and this is air. Being very being a bit of Picasso today. See, upwards, positive, I guess, right? And so when we talk about these two systems, they're no different from each other. I guess the top one, the other curve, I'll draw as green because it's an amalgamation between the red and green. And the point for doing this is that this capillary pressure merely scales as a function of, scales with elevation. So capillary pressure would be equal to the elevation multiplied by the difference in the densities of the fluids, or the unit weights. And I guess for this one it would be the difference between non-wetting minus the wetting. And so here this would be, the wetting fluid would be water, so non-wetting would be air, and the wetting would be water. Blue, I guess, right? And below here, the wetting would be water, and the non-wetting would be the apple. And so the idea is that when you want to be able to evaluate these capillary pressure differences, then I'm going to do it kind of neutrally here. It's going to be elevation multiplied by the difference between the two pressures, and it's going to, the non-wetting is air, so it'd be the unit weight of air minus the unit weight of water. And down here, I guess the capillary pressure would be increasing downwards from this point, and the capillary pressure again would be the elevation multiplied by the difference in the unit weights. The wetting fluid, non-wetting fluid would be the napple. Can't move it over. And the other one would be water. So that's the basic idea. And so when it comes down to calculating these behaviors, it's just given by the difference. This difference here would be the capillary pressure. P napple minus P water. And here it would be this amount, which is capillary pressure, which is the difference between the air minus the water. So they're absolutely uniform concepts. And so the idea is that the pressures, if you had all these three phases continuous and they're connected from the surface, so in other words, I suppose this would, so this is, I guess I should also say that this is the water table. And I suppose I should say that this axis here is pressure, right, as you go down in each of these. So by definition, we said that the definition of a water table, or an oil table, is, and an oil table as well, is where the pressure is atmospheric. So by definition, these, if they were the surface of something, would have to all go through there. So for instance, you could think of this as looking like a ganglion of DNAPL that sits inside water. I guess around it. And I guess above here, you could think of this as green, I guess it was. You could think of this as being air that exists all the way up here. Don't know why I did that, but that's fine. That sits inside water. Again, blue outside. And so as long as you have both of those phases, and you can get from water to water continuously through the water only, and you can get from the air to the air through the air only, then this distribution of pressures is true, just like being in a swimming pool. It's no different from that. And they vary with elevation below the water table, where all of these are compressive. And they vary above the water table, where they're all, I hesitate to say tension. They're in tension relative to atmospheric pressure, but they're not in tension relative to absolute pressure. And so this air pressure, as you go up 10 meters, would be less than air pressure, atmospheric air pressure at zero. Not very much, because this slopes at 1,000th of the gradient that water does, but so it's basically the same. But it's pretty significant for water. You could imagine this as being able to take, the best analog I can think of is if you took a bucket of water that was 10 meters tall, and you physically pulled it up off the ground, then the tension that you would have to apply to this to pull it up as a pressure would be exactly equal to this amount here. And it's a tension. So it's just like pulling something up by the bootstraps. And so the water here, surprisingly, is in tension, and so at the grain scale. But anyway, these allow you to define these curves. And since we started with by talking about the fact that we're talking about unsaturated flow, I guess the other thing we should mention is that these saturations that we're talking about here are often referred to in terms of volumetric moisture contents, theta, which vary between 0, when there's no water in the place, and porosity. So I guess volumetric content means the volume of the fluid divided by the volume of the voids. Saturation is equal to the volume of the fluid divided by the volume of the total soil, grains and voids. And so that's the difference. And so in other words, when you fill up the porosity, this term is equal to other way around, isn't it? Sorry. Yeah. Which is it easier? Yeah, so other way around. The numbers are right, but the numbers are wrong. Saturation is a function of the void space, right? Saturation is equal to the volume of fluid over the volume of the voids. So that when it equals 1, it completely fills the pore space. And volumetric is the volume of the fluid again, but divided by the volume of the total soil, including the pore space and the solid grains as well. And so by definition, the maximum value of this can be when it completely fills the void space, which is the volume of the voids divided by the volume of the total soil, which by definition is the porosity. So that represents that behavior. So this is kind of important. So this is the transformation we've made. This is capillary pressure here. This is from a capillary pressure of 0 to a large number. And I guess you could imagine that since this is the air pressure, which is low, minus the unit weight of water, which is big, this would be a large negative value for the capillary pressure. And this would be a large positive value as you go down. Because we're going, really you're going from, because you're going in this direction, in this case negative, in this case you're going in this direction, which is positive. So that's worthwhile figuring out. So when we look at the capillary pressure versus saturation curves, it just happens that if you have two fluids, one happens to be a gas and one happens to be a liquid in this case, and these two happen to be liquids, then you get the same behaviors. They happen just to be fluids that we're interested in. And so we can use that to try and understand exactly what's going in the subsurface. And so what we can do is we can look at some interesting ways of redefining those capillary pressure versus saturation curves. And I won't add it here, but I will note that you can add, of course, onto the base of this, these relative permeability curves, right? Which you know. And those apply both to these systems where we've talked about water, and I guess we did water the other way around, so that's switched, but that's fine. Let's not worry about it. So relative permeability and versus these same coordinates. And I guess we should make the point that we can think of capillary pressure also in terms of this matrix potential. So capillary pressure divided by unit weight is matrix potential. And so all we're going to do is we're going to make a switch to looking in the vadose zone, which is this, the unsaturated zone. And we're going to characterize these capillary pressure versus saturation curves in two ways. One is by kind of classical way, which is named for its originators, Brooks and Corey, I think from Colorado State, who are working on agronomy in the 50s-ish, which allow us to think about these in a specific way. And another very empirical way by an originally Dutch scientist working in Irvine, California in the 1970s called Van Genuchten, who interestingly allowed us to calculate these empirically and also get both capillary pressure versus saturation curves, but also relate those to relative permeability curves for different materials, just by experimental correlations. So that's the two things that we're going to attempt to do today. So the first thing is to look at these capillary pressure versus saturation curves in maybe a slightly different way. And maybe I'm going to use a different, actually, let me do this. Yeah, all right, I'm going to start out. So I'm going to talk about these Brooks-Corey relationships. So let's switch to this. Didn't want to do it. So Brooks-Corey. And so these are the basic ideas, capillary pressure versus saturation curves. So what do I want to do? All right. So the first step then is maybe to look at, again, one of these curves once again. And if we just look at a single slither of this, as we've done before, we can think of this as capillary pressure. We can think of this as saturation of water between 0 and 1. We can think of this as volumetric moisture content between 0 and porosity, I suppose, as we've just said. We could also think of this as being the volumetric moisture content, which is saturated. And we could think about this bounding value here, which is the irreducible saturation of water, right? This water we can't get out of the system. It's going to be left in it. And I suppose we could define a value of this as the volumetric moisture content that represents the irreducible volumetric moisture content, just as a parallel to this. And so if we were to find ourselves somewhere on this diagram, then we could identify this length here as being equal to, and we'll call this the actual moisture content, volumetric moisture content. So this length here would be phi minus the irreducible moisture content by definition for that length, right? And this length here would be equal to the saturated fully this one minus this one. And so what we could do is we could think about using this to define the location of this ordinate relative to, as a function of this. So what Brooks-Corey does is essentially this. It says, let's assume that we don't care about this part of the graph, which is on the left side of the green line. So we're going to ignore this. So what we could do is we could draw that same diagram as before with the same curve on it. Whoops, gone too far. But when we think about the diagram, we're just going to draw it that starts here. Maybe I'll use this. And what we're going to do is we're going to start off and define this behavior on the bottom so that we start at the irreducible saturation of the water, which is defined as a volumetric moisture content, the location where it's fully saturated, and the location where we have a point, which I guess would be this point here, which would be the actual volumetric moisture content we have. And so what we could do is we could define an effective volumetric moisture content, which is equal to this term here divided by this term here. So theta minus irreducible saturation, bless you, divided by the saturated component minus, again, the irreducible saturation of that component. And so that allows us to be able to scale things just like we did for saturation. And so in the same way that we defined saturation before, this would be saturation, irreducible saturation, 100% saturation, and this would be, I suppose, the saturation we find ourselves. We could define an effective saturation which is equal to the same as these ratios. The saturation we're actually at, which is this point here, minus the irreducible saturation of water. And we're only interested in water here because this is partially saturated Vadose zone, no NAPLs involved. And this would be 1 minus irreducible saturation of water. This would be 1 because this point here is 1, right? So this, the equivalent of this term here, has to be just this. And so our interest in doing this is because if we only take this portion of the curve, which is what we're going to work with, then let's redraw this curve on its side. And so I'm going to take this curve here, this whole thing. We don't need to do that, but you get the picture. I'm not actually going to cut it. And I'm going to redraw it in a slightly different way. And it's going to be so that it's, again, it'll look similar. But it is rotated through a small amount. Actually, it isn't rotated, it's just the same, isn't it? But this now is between these ordinates. So this is an effective saturation of 0 and 1. So it's only spanning this particular length here. And if we put the same ordinates on the bottom, it's an effective moisture content, again, of 0 to 1. It's scaled in that way. And so this is capillary pressure on this side here. This is what we've called before our bubbling pressure, PC0, or P bubbling, I guess. And so now what we've done is we've removed the irrelevant part of this curve that we don't care because we can't really get there. Oh, I guess I've drawn this incorrectly, of course. This should be, it has to go all the way to the side. So I suppose that'll take out that full curve, but so that's how it needs to be. And so what we could do is a couple of things. One is we could divide capillary pressure through by unit weight of water, which is what we do. And so this bubbling pressure would also be just divided through by the unit weight of the wetting fluid in this case. And we could plot it in log-log space. And so the interesting thing that happens is if you plot it in log-log space, then this kind of curved portion of the curve here ends up plotting as a linear portion. And so this is capillary pressure over PC0. So if we do that, then if this is equal to 1 and 10 and 100, and if this is equal to volumetric moisture content or saturation, they should scale the same way, I guess. This would be equal to 1, and these would be logs, so this would be 0.1, 0.01, 10 to the minus 3, I guess, etc. Then what you find is that you get a curve that looks like this. And it turns out to be linear. So this is the same as this curve here. This and this are the same curve. So it just straightens it out. And so the interesting thing, so empirically, we don't know any reason why that should happen that way, but observationally, that's just what happens. And so the interest in doing that is that now this has a gradient that we can take over 1 log cycle. So if we take 1 log cycle, which is this, 1 log cycle, then this term here we call lambda, and as a result of that, I'm never going to need this derivation again, but merely to make the case that we can write this relationship as basically the equation of a straight line, which rises from some value when the saturation is equal to 1. And so the equation of that straight line should be something like the volumetric moisture content, which is exactly the same as the effective ones, are equal to the capillary pressure divided by the bubbling pressure to the power minus lambda. That's all. So that's just the equation of this straight line. This. And so that's Brooks-Corey. And so we haven't really used this, although we almost used it the other day. You remember when we were talking about depths of penetration of fluids. Remember we spent some time making this case that we could work out the magnitude of the depth of this floating product that sits on top of the water table. And we do that by realizing that we get a water table and an oil table, and the water table has to be at kind of atmospheric pressure. And so if we look at what happens immediately above the water table, it's kind of like a distribution of these capillary pressure curves, which is what we're investigating today. And we said that a more sophisticated way of just, rather than using this big block of a uniform saturation, would be to account for this variable saturation that occurs as you go up with height within the column, both of the water, the napple, and the air, and that there was a very complicated relationship that allowed us to be able to define what those thicknesses were, which we didn't go through. Well, those basically use the idea that you can take the capillary pressure curve that we've used before, which looks like this, and you can linearize it. And this linearization is just what we've done. It's the observation that if you plot this curve in log-log space, log capillary pressure versus log saturation, that all of a sudden it plots as a straight line. And if it plots as a straight line, then it has a very simple formula, which is not given there, but it's the one that we've just looked at on this page here. It's this very simple formula here. And if we have a simple formula to represent the behavior, then we can use it very easily to do some calculations, which we won't do, but you need to know about this, the existence of this particular curve. Okay? So that's where it comes from. So it's not voodoo. It comes rationally by doing a couple of things. Taking the normal capillary pressure versus saturation curve, cutting off the left-hand side, so the range is only between the irreducible saturation of water and completely saturated with water. Then you take the curve and you plot it on log-log space. It ends up being a straight line, and it comes out to a very simple relationship in log space. And so if we go back to our notes, then we can say something about what that means in terms of the behaviors. And like I suppose this really is the transformation here, is if you take four curves here on the left-hand side, they're all defined in terms of matrix potential, right? This is capillary pressure divided by unit weight, so this is matrix potential on this side. If I make it, didn't mean to make it that much. Don't know why it keeps on jumping, but it is. So this is matrix potential here, by definition. And these curves have different characteristics. So you could think about what these curves would mean in terms of the materials they are. So this happens to must have a high permeability because the bubbling pressure is really low, right? And so air can get into this sample. Air is the second fluid. This would be water saturated here, and the bubble that's going in here would be air that would be progressively going into the system. This would be less permeable. I suppose from the fact that this curve here is almost horizontal, it means that almost all the pore spaces in it are roughly the same size, because as soon as you saturate one of them, you saturate almost all of the porous medium. And that up here, this would have the lowest permeability. I guess I'm holding on to this too much. And because as you go up here, this is really quite steep, you have to provide a big extra pressure to get it this saturated. And so you have to provide a really big extra pressure to get it this saturated. And so this means that the initial small pore spaces have even much more smaller pore spaces as you start saturating the rest of the sample. So you can say something about the morphology of the pore space of the sample as you go through there, which makes sense. So most highest permeability, lowest permeability, and the slope of the curve says something about whether it's uniform pore sizes or what would be called well-graded pore sizes, I suppose. So you think about plotting these on a curve, again, of capillary pressure versus effective saturation. And of course, effective saturation is the same as effective volumetric moisture content. They are exactly the same as each other. Then you'd find that these curves would plot like this. So the one that has the earliest entry would be this one. You see this kind of initial tail on it here, which kind of plots here, which isn't a straight line. But the rest of it, which is the remainder of the curve, this part here, would correspond, I guess, to everything, really everything after that. And number 4, not surprisingly, would be the one that has both the highest invasion pressure, which is this, and in terms of the change in porosity as you go through it, the flatter, I guess the flatter this gradient, if the gradient was like this, it would mean that you have to apply a really big pressure now to invade it just a little bit. And so this would, the flatter this curve is, the steeper it would be on this curve. So you can see the mapping. So that's what's going on in this. So it's just a way of being able to define those behaviors. So probably spent more time on it than we needed to. But this basically says the same things we just said. Early, high permeability would give you early entry pressures. So you'd be over here at low pressures in terms of this. And flat would give a near vertical line. Lower permeabilities would mean that you have to apply a higher pressure to invade it, which is this. And as you invade it, the pore space is much more disparate in terms of bigger pores, really, really small pores, even smaller pores. And that means that this green line is flatter than the other one. So just the physical idea. So anyway, so those are used typically to be able to describe behaviors analytically and their kind of historical curiosity. The other thing I suppose that we might like to do is we might like to be able to figure out exactly what these capillary pressure curves look like without ever doing an experiment on a piece of soil, because you don't necessarily have that luxury to do that for your client. And so it'd be nice if we could find some way to be able to figure out exactly what these capillary pressure curves look like for different soils, and also by inference what they'd look like in this form. You can move one to the other. And it would also be nice to know what the relative permeability curves would be as well. And so one way to do that is to use these empirical relationships by Van Genuchten, which do just that. And so they allow you to be able to look at the volumetric moisture content as a function of capillary pressure. And all they are a recipe, if you like, from having done a whole bunch of experiments to measure these capillary pressure curves in different materials and to find out some relationships statistically between those materials and some parameters. So the idea is that you can define, these are, I guess, moisture content versus capillary pressure curves, or saturation versus capillary pressure curves. I guess these could also be matrix potential curves, right? This is the same as matrix potential. And the idea is that if you can define the shape of the curves, you can fit a series of parameters to them. And so the effective moisture content is linked to the matrix potential. So these are the two parameters that exist on this curve here, right? Plotted just in normal space, not in log space. And they're a function of, three parameters. And those parameters are m, n, and alpha. And they're just fitting parameters, nothing more than that. You can think about it being plotted in terms of volumetric moisture content and matrix potential. So this is psi, or log psi. Or I guess still here. Or you can do it in terms of saturation, because we've made the point, I guess, that effective saturation and volumetric moisture content, effective volumetric moisture content, are the same. And so these equations, of course, should be identical, and they are. Just by inspection, you can see that that's the case. And also you can see that saturation is as well, once it's corrected for irreducible saturation. And then the rest becomes just a curve fitting property. And so the idea is that you could do it in the forward direction, in which case if you imagine having a curve that looks like this, where you have the physical shape of the curve that you know. So if you know what this curve is on this plot, then you might want to calculate what these controlling properties m, n, and alpha are. Less likely that you'd want to do that, but you can do, and it's just by a recipe. And the recipe is just as given in Fetter, and the idea is just this. You take the curve that you have, which is a real data curve. it must have a porosity in this particular case of 50%, right? Because this is the fully saturated, 100% saturated part. It must have an irreducible saturation of water content of 0.1. And these are the magnitudes of the pressure head. So this is the same as matrix potential. So this is PC over gamma W, this term here. And the recipe to get the terms M, N, and alpha are to do this. So first of all, you take the curve and you isolate these N-member moisture contents here and here, which are the saturated moisture content and the residual moisture content, right? This is R and this is saturated. Difference between them, or no, the average of them, I guess, the midpoint between them. So add them and divide by 2. And so in this case, 0.5 plus 0.1 is 0.6, divided by 2 is 0.3. You define the slope of this curve at this point, intermediate point. So this ordinate here is 0.3. So this point here is 0.3. So you define the tangent to the curve at that point. You look at that between one cycle, log cycle, in matrix potential. So this is 10 to the minus 4, no, 10 to the 4, sorry. This is 10 to the 2. So this must be 10 to the 3. So this, by definition, is one cycle. So in other words, you have one length here, which is this. And you have one length here, which is this, which are, I'm just overwriting these components, right? And so you find out the slope of this at this particular point. And so that is equal to 0.34, just looking at the grade of that. You take that slope, which is 0.34, and you divide it by this length between these two moisture contents, which is 0.5 minus 0.1, which is 0.4, which gives you 0.85. And then you look for where that value is. If the value is between 0 and 1, then you use this expression to substitute this into here and get a value of m. If it's not, then you substitute it into this differently. And once you have the value of m, then you can substitute it into this empirical equation and get a value of n. And once you have a value of n, then you can substitute m and m into this equation and get a value of alpha. So you have the three values you have. And so it's not very likely that you'd want to do that, because we'll usually use it in the a different way. But the useful thing, if you look at this, I guess the one important thing to remember from this is that this value of alpha is basically equal to 1 over the entry pressure, 1 over the bubbling pressure, PC0, divided by unit weight. And so you could think of this as what we've referred to before, I think, as HC0, the height of head of water that it would take to push a bubble of air into the system. So that's the one thing that comes out of this. So it's a recipe. So I'm not sure you'd ever have to use it, but the point is that if you have a curve that you know what it looks like, by limiting between the irreducible saturation of water and its maximum saturation, you can look at the slope and the coordinates of the graph, and you can get these parameters. The most useful way to use this is the opposite direction. And that is to realize that for a variety of different materials, kind of described here in a narrative, is that for clays through sands, then you can define magnitudes of the parameters that define these individual terms. And, in the terminology that we've already used, the value of n that we've used before is actually beta in this term. The value of alpha we used before, which we said is the reciprocal of height. It's 1 over, actually it's 1 over h0. This is equal to 1 over this. It's units of 1 over length, right? Because of this term here is basically hc0. And so the units of this are that. And you have values for what we referred before as the saturated moisture content, which would be the same as porosity, I suppose. And the residual moisture content of water, which would be theta W0, I guess we've called it. And so for these individual terms, all these individual values, we can use, and gamma. Where's gamma? Gamma we must be able to calculate as a function of those other properties. And so the idea is that you can use these curves in the same way. So now we know what the values of these individual terms m, n, and alpha are. You could reconstruct these curves as a function of capillary pressure and effective moisture content or saturation, right? So if you know what these values of m, n, and alpha are, you could make the curve here. You don't need it to start with. But perhaps more importantly, and as we alluded to, is that we would like to be able to figure out what permeabilities are for these relative permeabilities. And so we can also get the relative permeability that represent these behaviors by looking at this term here, which is just given empirically as this. This would be the equivalent of what we've called K sub r to water as a function of volumetric moisture content, or it could be as a function of saturation, I suppose, is what we've thought about it. And that is, it's a function of effective saturation, and it's a function of these parameters of m, I guess only of m in this particular case. And so in other words, if you know what your saturation is that you find yourself at, so it's if we write it in terms of effective saturation is the saturation you are at in the sample minus the irreducible saturation of water divided by 1 minus the irreducible saturation of water. So in other words, this would be the saturation you're at in the ground. These are merely parameters. Then if you know the value of m for your material, which you can get from these curves that we looked at here, then you're able to figure out exactly what the capillary pressure versus saturation curves looks like. So in other words, this would look something like questions. It would look like this, right? It's only for the water phase. The air phase in the unsaturated zone we don't care about, because the conductivity in the air phase is so much higher than the water phase, because its air is the fluid that's going. And so typically we only care about the aqueous phase. So actually, what was I going to do? I'm not sure what I was going to do right then. I've lost my train of thought. So this now is defined as a function of this m parameter and of the effective saturation. And I missed it somewhere up here, but m is a function of n. And so all by way of saying is, if you want to calculate this relative permeability curve, you need to figure out what your soil is. You need to figure out what the value of n is for that soil. If you know what n is, then you know this. and you can calculate the value of M. And if you know the value of, yeah, I was going to say, and if you know the value of M, it looks like that's the only value you need to be able to calculate this, which is the relative permeability, this curve here. And so you have an immediate way of being able to define the relative permeability curves and the capillary pressure versus saturation curves, at least for the liquid phase, only for the liquid phase in this particular case, by using this empirical relationship. And so it's quite a powerful technique in that regard. So not sure you have to do that in this class, but at least you know that the basic idea is that you can get these curves that define behavior. And we've made the point before, I suppose, earlier on, that this, not this, that these are the two principal relationships we'd like to be able to understand to represent flow in our system. So I suppose what we've done here is that we've at least made sure that the curves that we can get empirically, just by using some soil classification, are this, maybe I'll do it even larger, even more blunt, are this curve here in terms of what it looks like, and this curve here in terms of what it looks like. And so we might not be able to do everything for all the components that we're interested in defining behavior for, but we can at least do it for the water. And so by inference, we have this component that we're able to now, if we wanted to, which I guess is not a bad segue into what we'll do next. And so we've made the point that if we're in a portion of this aquifer, which is partially saturated with NAPL, we know a portion, this is fully saturated now, and so if a portion of it is saturated with the NAPL that fills up the pore space, then we have some way from these capillary pressure versus relative permeability curves, and capillary pressure versus saturation curves, and capillary pressure versus relative permeability curves, to be able to define this volumetric flow rate, because we have this for a given saturation. And if we have this volumetric flow rate, and we know what the contaminants are that are dissolving, we can make a linkage to be able to evaluate the mass flow rates that come out of the system as well. So that's kind of the logic of the workflow, if you like, in going through this. And so that's the last thing that we'll really do in terms of looking at free phase behavior. And so we started off in week 1 saying that we'll look at the first couple of months where you drop this stuff into the subsurface. It does what it does in going where it goes. It's controlled really by interfacial tension in where it goes. That's the big force that controls behavior. And that the distribution and architecture of it is controlled by these pressure versus saturation curves that we've talked in length about. Fluid transmission through there is controlled by these relative permeability curves, and if we know what those look like, and we know what the actual permeabilities are for these materials, so in other words, the permeability of this sand or aquifer that we have here, then we can use relative permeability to calculate this flow rate. In most of these circumstances, we're not going to change the distribution of these free phase fluids. They're going to stay there, they're not going to budge. But the next thing that we'll talk about now is what are the rates at which this will dissolve from here, and how quickly can it get carried downstream, and what concentrations will it arrive downstream, and what are the factors that might change those concentrations in terms of sorption of the dissolved components onto the solid grains that don't move. And so when we talk about the next topic, which will be on contaminant transport, we'll look at different mechanisms by which it gets carried downstream. So now you should make a mental break between two different fluids flowing, maybe water invading the vadose zone, an air-filled porous medium, and establishing an equilibrium with some water and some air, or a saturated groundwater zone being invaded by a NAPL and establishing an equilibrium with lenses of that NAPL and the chimneys of the NAPL in relatively low saturations. Now we're going to assume that those basically stay in place, they don't move, but water moves in each of those cases. And if water moves, then it can dissolve the components and carry them downstream. And if we do that, then we need to look at a different set of transport mechanisms. One where diffusion occurs by the NAPL diffusing into the liquid, and also the liquid moves with that dissolved component and carries it downstream. So that's our next task on this. Okay.